Alright guys, welcome to the video on LeChatelier's principle. This is the second part of 6.4. In this video what we're going to be doing is we're going to be going through the three examples that are at the end of your notes. So you should have already watched video 6.4. That was the conceptual information regarding LeChatelier's principle. This video is now three specific examples regarding how equilibrium shifts. So this example says consider the following equilibrium for which delta H is less than 0. So I'm going to underline this for now. It's probably going to be important. And they give us the reaction. So we have reactants and we have the products. Then it says, how will each of the following changes affect an equilibrium mixture of the three gases? And they give us A through F, different changes. So A says if O2 gas is added to the system. So if O2 gas is added to the system, means we're adding more reactant. Well, now we've shifted equilibrium. Okay, we now don't have the right amount of products to reactants. We don't have that correct ratio to equal Kc or Kp. Now instead we have too much reactant. So what we need to do is we need to somehow get this back to equilibrium. So what we need to do is we need to use up this reactant that we added. So we have to use up the reactant to make more product. So what we say is that equilibrium shifts to the right. We now make more product because there's too much oxygen to be at equilibrium, so that extra O2 needs to be used up. So we're using up SO2 and O2, and we're creating more SO3. And then B says the reaction mixture is heated. So what we need to do first, before we figure out the effective temperature, is we need to know if it's exothermic or endothermic. So up here, delta H is less than 0. What does that mean? That means that it's exothermic. So I want you next to this delta H, write exothermic. If it's exothermic, what does that mean about heat or energy? Means that it's released, which means that heat is a product. So we can actually think about it as 2SO3 plus heat on the product side. So if the reaction mixture is heated, that means that we add more product. We now have more heat than is necessary for equilibrium. So what we need to do is we need to use up this extra heat that we've just added, which means it's going to shift toward the reactants. So it's going to shift left. And that's because, again, heat is a product, so adding heat is like adding extra product, and we need to use that up. So it's going to shift to the left. So what we're going to do now is we're going to use up that heat, we're going to use up SO3, we're going to create more SO2 and more O2. And then C says the volume of the reaction vessel is doubled. So if we have a volume, it's doubled. What does that do to pressure? And that decreases the pressure. You increase the volume, there's more space to move around, that decreases the pressure. When you decrease the pressure, what you need to do in order to counteract that change is you need to shift to the side with more moles of gas, because that's going to essentially increase the pressure back up. You have more collisions. So if you are decreasing the pressure, count moles of gas. We have 3 on the reactants, 2 on the products. So it's actually going to shift left, because when we increase the volume and decrease the pressure, it's going to go to the side with more moles of gas, which is the left side. Okay, so if that's the case, what we can say is that we make more reactants and we use up the products because it shifts left. D says that a catalyst is added to the mixture. Well, what does a catalyst do? It speeds up the reaction. So even though it speeds up the reaction, that's based on kinetics. Equilibrium is not based on kinetics. All it's going to do is it's going to change the speed to reach equilibrium. It's not going to change what's in that equilibrium mixture. So adding a catalyst actually has no effect. It only affects the rate. And then E says the total pressure of the system is increased by adding a noble gas. Now, we're changing pressure. Okay, that is true. We're changing the total pressure of the system, but we're adding a noble gas. Is there a noble gas anywhere in this reaction? No. We're not adding anything to this equilibrium mixture, which means adding a noble gas, which is also something that doesn't even react, isn't going to affect this. We're not adding anything that's in the equilibrium mixture. And then F says that SO3 gas is removed from the system. So this SO3, we're taking some of this away. Okay, so now we don't have enough SO3 to be at equilibrium. So what do we need to do? Well, we need to make more SO3. So it's going to shift right. Okay, so we do not have enough, I should say, products. Okay, we don't have enough products. We need to make more products, so it's going to shift to the right. Okay, so that's example 1. Now example 2 says, how do the following changes affect the value of the equilibrium constant for a gas phase exothermic reaction? Okay, so we have these 4 changes. It wants to know, how does it affect the equilibrium constant? Okay, this is KEQ or KC or KP for a gas phase exothermic reaction. So if we remove a reactant or a product, how does that change the constant? Well, it doesn't have an effect. Okay, the equilibrium constant is a constant. The only thing it depends on is temperature. Anything else will not affect the equilibrium constant. So if you remove a reactant or a product, it doesn't have an effect. If you decrease the volume, it doesn't have an effect. But if you decrease the temperature, what we need to realize now is this is exothermic. Heat is a product. So if you decrease the temperature, what you're going to be doing is you are going to actually increase KEQ because, again, heat in exothermic is a product. So if you decrease the temperature, you're taking away product, which means it has to shift to the right in order to make more heat, which means now when it comes to the constant, you have a bigger number on top, you have a smaller number on the bottom, so you're actually going to be increasing KEQ. And that's because it's an exothermic reaction. If it was endothermic, notice it would be a direct relationship. This is something that's very important. They will try to trick you. The only thing that affects the equilibrium constant is temperature. Anything else does not change it. So adding a catalyst will not have an effect on the equilibrium constant. It only affects the speed that we get to equilibrium, not the constant itself. So for example number 3, what I want you to do is I want you to actually try to fill this in. So I want you to fill in the following table where you're looking at how the reaction shifts and how it changes the equilibrium constant. So fill this in, pause the video, fill this in, work through everything. If you need to draw arrows using this reaction at the top, and then play the video again to go through the rest of the answers. So for this reaction, we have the delta H. Delta H is positive 111. Okay, that is endothermic. Okay, that's endothermic. So heat is a reactant. Okay, we add heat to the reactant side. So let's look at this now. If we add PCl5, okay, now we have too much PCl5, reaction is going to shift right. Okay, we have too much reactant, we have to use that up for more products. And then we are simply changing a concentration, so there's no effect in K. Then what if we remove Cl2? Now we don't have enough Cl2, we don't have enough product, so we now need to shift it to make more product, so it's going to shift to the right. Again, K is not changing because the only thing it depends on is temperature. The third change says to add argon. Well, is argon anywhere in this reaction? No. Right? Argon is a noble gas, it doesn't react, and it's nowhere in this equilibrium mixture, so it's not going to have any shift. It's just going to stay the same. And again, there's no change in K. So next we decrease the pressure. Okay, so now you're decreasing the pressure. So to counteract that decrease in pressure, you don't have enough collisions now, we now need to counteract it to increase the number of collisions back up. So we're going to shift to the side with more moles of gas, which in this case is the right. And again, changing concentration, changing pressure has no effect on K. Now we increase the temperature. So we increase the temperature, that means we're adding heat to the reactant side. We have too much reactant now. So now what has to happen because we have too much reactant is we need to use that up, so it's going to shift to the right. Now, because this is an endothermic reaction, we're increasing the temperature, right? So we're increasing the temperature here. We have too much reactant, which means it's going to shift to make more product, which means in your KEQ, you now have more products on top than reactants on bottom, so your K is going to increase. Okay, next thing says to add a catalyst. Well, how does adding a catalyst affect this? Okay, all it has it do is go faster. So it's not going to shift the equilibrium at all. You're not going to shift to the left or the right because you're not adding or taking away reactants or products. You're simply making equilibrium occur faster. And again, it doesn't change your K. And then if you decrease the volume of the container, so you have a container, you decrease it, what have you done to pressure? You've increased the pressure. So because you've increased the pressure now you have too many collisions. So now what you need to do is you need to counteract that change by reducing the number of collisions. So we need to shift to the side with the lower number of moles of gas. That means that we shift to the left. And again, it does not change K. The only thing that changes K is temperature. So that is it for these examples. If you have any questions, let me know. Otherwise, you'll be good to go for the LeChatelier's principle worksheet that you're going to work on.